So, continuing from where we stopped, velocity of mechanical wave is a function of elastic modulus and density, therefore, it can give you some idea about the soundness of the concrete. Now, how do you measure them? You can actually have what is called a direct measurement, like this is your section. You usually will have a transducer and a receiver, right. I suppose I have a diagram, yes, it will look something like this. I will come back to that slide later on. So, you have a transducer and a receiver. Now, this transducer is connected to a pulse generator, which will generate the ultrasonic pulses, some sort of oscillator, and then converts this electrical energy into mechanical waves, right. So, this pulse generator and this is a receiver. Then obviously, this receiver again converts this electrical transducer converts electrical pulses into mechanical pulses, and this receives the mechanical pulses and then converts them into electrical signal, again is amplified. Then actually you are trying to measure the time of travel. You actually measure the time of travel. So, there is a time measuring circuit, right. So, basically this is received one and this is the input one. So, what is the time delay between these two, that is what you find out, and then there must be some sort of a display unit. So, basically you switch it on and therefore, pulse is generated and there is a transducer. So, this is your section. So, this kind of a measurement is simply the direct measurement. You put the transducer on one side and the receiver just exactly opposite to the other side in the specimen. So, that is called a direct measurement, right. So, direct measurements, it actually measures time, but today modern instruments will have a digital display. So, it would ask for an input of the thickness of the section, this dimension. So, if this dimension you input it, it will straight away calculate the velocity and give it. In good old days, this will give in microsecond. It will give you time of travel through this path in microseconds, and you know the length, so you calculate out the velocity yourself. Now, this is direct measurements. You can even have indirect measurement, because all the places you may not get both the sides of the section, right, both the sides of a section. For example, some column, I have a column and let us say I have wall on this side, wall on this side, both the sides I have wall, walls on this side, or it is not available for whatever reason. Then I want to find out what is the ultrasound pulse velocity in this. So, I can put transducer here, receiver there, transducer here, receiver there. Now, this will be the path length then. So, your input path length will be given by, since you know this dimension, therefore, you can find out the path length. So, this is called semi-direct measurement, something like this, semi-direct measurements, you can use it in corner. But you can also do, for example, a basement wall or something, only one side is available, then you can do what is called indirect measurement. So, put the transducer and receiver in the same, but then remember only a small what you call S wave, surface wave will reach here, and it is usually the percentage is very little, it is around 3% of the total energy that goes like this, and usually velocity of this wave is less than the velocity of P wave or the direct this wave. So, this you cannot you cannot compare this measurement result with this measurement result, because this will be measuring only the surface wave, right, whereas this is direct measurement and the velocity is less. So, therefore, they cannot be compared, but you want to compare this with another place where you have done this measurement, that is possible. But this will not also not give you information about the complete section, this will give you information about the complete section, this will give you the information about the complete section. For example, if there are voids here, bad concrete in the core, you will get in more information about this, while this will give you information about the surface concrete, all right. So, what you do is in such situation what we do is okay. So, this formula anyway I just mentioned already. So, what you do is in such situation we place it indirect measurement, right, in a slab. So, what you do is we measure at fixed spacing, say 75. So, you have transducer placed here T, receiver 1 R 1, then place again, shift the receiver R 2, then shift the receiver to R 3 positions, something like this, right. Then travel time, if you plot, travel time will increase when you are making measurement, indirect measurement, travel time will increase, and it is expected to increase linearly if the velocity is constant. So, therefore, you can find out the slope of this one, and 1 over that slope will give you the velocity, because this side is the spacing, this side is the travel time, spacing versus travel time. So, distance divided by time will give you the velocity. So, you can actually make measurements at different places. This will be more relatively more reliable than taking single point measurement. So, this is how you can measure actually indirect measurement, but this can all be used for comparison. You can also estimate crack depth. How? Simply measure, this is your crack, and this is what we actually used in one of the cases of the segment we talked about. So, one could find out, or in many places you can use. What you do? First you place your transducer at this position and receiver at this position at some equal distance. Then shift it to some distance here y, and this also shift to the same distance. From the geometry, if this is the height of the crack, from the geometry simply time of travel in both the cases are known. So, in this case, since this is void, the receiver will measure the time, the earliest time. Receiver will measure the short time required to travel through the shortest distance, because through this air gap is there, the velocity will become very less, and this wave will reach much later. So, it will first recognize this one quickly. So, the path is simply h square plus x square divided by so if you see, since the velocity is same in both the cases, then this too should be same. In this case, path is y square plus h square under root, right, y square plus h square under root, and twice of this divided by t 2, that is the velocity distance traveled, and in this case, first case distance travel is this much, and therefore, one can obtain value of h, one can obtain the value of h. So, crack depth you can measure using this kind of technique, particularly on flat surfaces. If it is vertical surface, same technique you can use and you can find it out. So, crack depth can also be measured or estimated rather using this method, right. You can also do it by some other means. What you do? In that case, in another case, what you do is you take like same principle. Here is your crack. So, I have a transducer here, receiver point R 1, then receiver point R 2, receiver point R 3, etc. So, up to this I will have surface wave like this. Beyond this, actually beyond this what will happen? Beyond this it will travel in this manner, right, beyond this, because through the crack it will take longer time. So, it will not register that, and then if you find, you will find that on this side the measurements taken on the left hand side or one side of the crack at equal spacing, it gives you a line like this, and after some point the slope simply changes, and this is your crack distance from your transducer point. This is the crack distance from the transducer point which you have measured at the space you are able to see. So, there is a change like this. From this difference you can again find out the crack using geometry. The formula is given here. Using geometry you can derive it, is not a very difficult one. H L divided by T. So, L is this distance, and T 2 by T 1 measurement time minus T etc., etc. So, ordinates are the ordinates, this is T 1 T 2, these are the in T 2 and T 1 are the ordinates in time axis, at the crack point such that T is equals to T1 minus T2, T2 minus T1, and L are the slopes here. L are the slopes of the line at time equals to 0, and L is the this is not. So, L is the distance from this is L, this is L, and T2 minus T1 is T, and this value I am calling as T2, this value as T1. So, from this one can actually find out the crack depth as well. So, this is how you can actually measure the crack, but I think the previous one was simpler, much simpler to understand, right. So, also you can find out layer thickness. For example, in pavement, supposing you have put a lean concrete, and then you have got or some other or just the concrete thickness, rigid pavement thickness you want to find out. Below is another layer. Then you can use this concept again using ultrasonic pulse velocity, you can find it out. Ultrasonic pulse velocity you can find it out, you can find it out. How? This is your layer thickness, let us say, this is a layer thickness. So, put your transducer here, then the receiver points, several receiver points, measure. What will happen is, this is your this is the transducer, receiver points. Now, surface wave will travel like this, and as further it goes, before this wave can reach, it might reach back after reflection through the solid concrete. So, in that case you can find out the layer thickness as well. Suddenly you will find that there is a change in the slope. Initially the slope was something like this, then there is a change in the slope, and thickness of the layer is given by this sort of formula. T is equals to x by 2 V 2 minus V 1, x is the distance spacing, equal spacing. For example, V 2 by V 1, this is a slope, this is other slope, the slopes are different because suddenly there will be a change in slope. Now V 2 velocity, this velocity divided by this velocity, this ratio is being found out from the slope. Now, spacing is, if spacing is x, right, spacing is x. So, this case it will be x by t x square by t, and this is divided by, in this case it will be simply x by x, travel distance is x. In this case x square plus t square under root, in this case half x square. So, this spacing where you are finding there is a change in slope. So, half x by 2, this distance is x, half x by 2, and x is the relative spacing when you are travelling like this. So, depending upon this, velocity ratio can be found out in this manner. So, t could be found out from V 2 minus V 1 divided by V 2 plus V 1, etc., etc. So, one can get the layer thickness based on this concept, assuming that V 2 is much larger than V 1, is larger than V 1. So, one can actually use the geometry to find out. Okay. Just a minute, something else I want to tell, related to this. All right, this I have already explained, this. So, spacing also you can determine also spacing. Now, V is equals to f into lambda, velocity into frequency. So, size must be greater than lambda, that is what I said, for assumption of material being macro homogeneous, right. It should be homogeneous because I am assuming concrete to be homogeneous. MSA shall be less than lambda to avoid resonance and energy loss. So, if 54 kilohertz, supposing my velocity is 3.8 kilometer per second, my frequency will be 70 mm. 110 hertz this, and etc., and if the velocity is 4.6 kilometer per second for higher better concrete, these values. So, you can see that these are the kind of frequencies normally people use in ultrasonic pulse velocity measurement of concrete. So, machines will have either 110 kilohertz or 54 kilohertz frequency machine, and these are the dimensions, millimeter dimensions, specimen dimensions. So, there is a restriction on specimen dimensions which you can measure. Now, you can measure in thin sections provided with higher frequencies as well. So, that is the idea. It is simply calculated based on this, assuming this 4.6 divided by 54 kilohertz. So, 4.6 kilometer per second, it will give you 4.6 divided by 54 corresponds to 4.6 kilometer. So, 4,600 divided by 54,000, and then convert the distance that you get in millimeter. This is how you will get it. So, that is what it is. So, what are the factors which influence the results? Temperature, some stress history sometime, path length, obviously you know, but important is moisture condition. If there is a moisture, you will get different results. If there is a reinforcement present, it will modify your result, right, because velocity in steel is much higher. So, if you have a longitudinal rebar and you are placing your transducer here T1 T and receiver here, in fact it will not, before it travels through this, it will travel through this and you will get a much less travel time. So, corrections are needed if you have reinforcement, but normally you do not measure, you measure like this, you measure like this. No? So, bar would be either like this. So, you usually measure like this along this direction. So, bar will be something like this, or there may be a stirrup, but normally you can avoid the stirrup places. Bar will be something like this. If the bar diameter is less than 20, you do not need to bother about them, because this is too small compared to the section, but if the bar diameter is sufficiently large, you may have to apply some corrections. So, you can get idea about the soundness of the concrete, elastic modulus and density, how solid it is, how porous it is. Lower velocity means porous, higher velocity means solid and sound concrete. But you want to get the strength, then strength there is a little bit of problem, because it is not relationship between the velocity of mechanical waves or ultrasonic pulses, ultrasonic pulse velocity and strength. This is usually not linear, non-linear, and extrapolation becomes very difficult, because you can understand from the fact, supposing I have velocity and strength on this side and it is some curvilinear something like this, and I have been able to measure only in this range. My prediction can go anywhere wrong. Future I try to predict on this basis, I will not be correct. So, therefore, it is never it is not really used alone for strength, but together with rebound number, then you can do it. Indian code, for example, 1331, part 1 and 2 gives both these tests actually. So, part 1 and 2. So, what you can do is, but this test is needed in order to a calibration with rebound number also, because rebound number gives you only indication of the surface concrete, surface hardness, while this can give you indication of the concrete inside the section. So, first you test and do it ultrasonic pulse velocity test, and if you find the concrete is sufficiently sound in the core, then you can develop a rebound hammer correlation to predict strength. So, that is the idea, right. So, rebar effect is important. Effect of rebar, if it is along the direction, then you need some corrections, which would actually, because it will travel through this. So, velocity in steel then becomes important. So, if because it will travel through this path, so correction is needed. Velocity has to be corrected using this kind of a formula, where A, this is A length, this length is A. So, the travel distance is A plus the distance of the A plus the length of the steel bar, right. So, velocity of steel, which is around 5.6 kilometer per second. So, velocity in concrete one has to find out the A is this distance, L is this length. So, based on this you can find out, right. So, for A by L less than 1.15. Otherwise, measured velocity must be multiplied by a factor k, where k is given as gamma plus twice A by L 1 minus gamma square. So, this sort of curves are available from, for example, this is a butt diameter versus velocity, which is velocity of concrete divided by ratio of velocity of concrete divided by velocity in steel. So, this sort of curves are available for various diameters for measured values. So, one can use this kind of curves to estimate the correction, but normally we do not place here unless in precast units in a beam, precast beam or something like that, otherwise you do not place it like this. So, the other correction is, this is important, you might find this sort of thing, right. This is where this is common, and in such case it is actually British code gives you some ideas. Up to about 20 mm butt dia, practically you do not need much. Some other code gives you, Rylam gives you some correction like this 0.9 or 0.85 or something, and in some other, so depending upon the butt diameter, some other cases they give you the correction factors. Up to 20 mm or maybe about some 8 mm, 20 mm, you will not need actually much of a correction, but there will be some correction needed. Best is to avoid the rebar location if you can. So, you measure, change your place and see the velocity is coming lower, that value you take rather than where it is coming high. So, that is about ultrasound, ultrasonic pulse velocity test. You can not only measure get idea about the soundness of the concrete, and interpretation, code gives you some interpretation, the velocity, if it is more than 3 km per second, the concrete is acceptable. If it is less than 3 km per second, it says doubtful concrete, and anything above 4.5 is an excellent concrete. So, I will have a table later on when I talk of interpretation. So, this is what ultrasonic pulse velocity test and what it can do. The next test let us look at is pull out test, right. Now, this is becoming this is becoming quite popular, although it is there for quite some time, but the instruments developed and their calibration. For example, in US they have been, North America they have been using quite a bit, Europe there has been development, and now there are there are varieties of instruments available, obviously developed abroad in India and many other places maybe. So, a pull out test is something like this. What it does it? You drill a small hole into the concrete, right. So, this is your concrete surface, you drill a small hole, and the instrument is there which can actually cut a groove like thing. It can cut a groove, it can cut a groove, it can cut a groove into the concrete, and this pull out device, it will have a kind of a flange here, right. Then this is pulled out with a reaction taken, you press it from top, press it here and pull out here, press it here and pull out here. So, what happens, this flange which is there, order of these dimensions you can see is 25 millimeter. So, this dimension is simply 25 millimeter. This depth is also fairly small, as you can see, this is around, this diameter is 55 mm, and it would actually cause fracture of the concrete, a fracture cone would be there, and it would fracture in this manner. That means, this concrete will, because you are pushing here and pulling through this, so this concrete will tend to come out. So, in fact, this concrete is subjected to, the concrete in this zone is subjected to a kind of compression. So, the tension will be in the normal direction, which causes cracking, then this comes out. So, since you are actually crushing it in a way sort of subjecting it to compression, the result that you get is a measure of the compression strength, So, that is the idea of the pull out test. So, you got to have something like this. Now, you can test, this is called pull off test. You can actually measure the tensile strength of concrete, surface concrete. So, bond it here, the same instrument can do the job. Bond is sort of a 50 mm diameter sort of a disc, and bond it here with epoxy, pull it, it will take a chunk of concrete out. So, this it gives you an indication of the tensile strength, So, because it will fail directly under, you are trying to pull this concrete. So, you are subjecting it to tension, or you can do a partial core, just drill, but do not break the core. So, then put epoxy, bond it and use this disc, pull it out, it will break from here, will be a measure of tensile strength. So, you can actually get some idea about the compressive strength as well as idea about the tensile strength, and you need to have calibration. It looks something like this. So, this is how it looks like, right. This is how it looks like. You pull it like this, 25 mm here, 55 mm is this, and 25 mm. So, you are trying to pull like this, this is the flange, it pulls it, and as it pulls, the pull out force can be correlated to strength. So, core strength versus estimated strength, people have estimated strength from this cut and pull out test, capo test, cut and pull out test, capo, cut and pull out, cut and pull out, cut and pull out test, capo test. This is developed in Scandinavia basically. So, that is they have actually commercial equipment available are developed there, and seems to be fairly successful. So, you get some sort of correlation between the core strength you can get. Core strength, red ones are the capo test result, this is the core. So, 45-degree line is here, right. So, 10, 10, 45-degree line is here, and apparently the capo results match with the core quite well, while rebound hammer prediction may not go well. As I said, it can go well provided you have your own correlation. You just can't do the rebound hammer test and predict the strength. You have to do a lot more work, use some cores together with this. So, that is what it is. So, this is how the pull out test looks like, right, and you can put it during the casting also. So, this is the insert you put in during casting. This is the insert that you put in, this is your formwork, this is threaded, and this insert has gone right in the beginning, right, and then after the concrete has partially set, before final setting, you just unscrew it and take it out. So, this hole remains, and this one also remains. Then you put your pull out rod, which can get threaded here. So, you just put it and thread it off, right, and then pull it out in the same manner as you have done. So, in this way you can actually determine the strength development in concrete. So, if you have done this, put this insert right in the time of casting, you can actually also find out the strength development also. You can find out the, this is same 25 mm, 25 mm, 55 mm, etc., this remains same, right. So, this one could actually, people have done some analysis, and this is the finite element analysis, fracture analysis and all that, and by doing this one could see the kind of stress developed, fracture plane developed and all. It matches by and large with this. So, it matches by and large with the theoretical and experimental results by and large matches. So, that is the claim, claim of the manufacturer, and we did ourselves did some test and we found that it does a good job. So, basically correlation can be established, the force required to pull out. Force required to pull out is a measure of the compressive strength. So, some sort of correlation with 150 mm cube one can get with different types of aggregate, and these are available. So, we actually did some tests and of different types of cement and all that, and we did find that it gives you an error within plus minus 10% of the core result. So, for example, coarse aggregate type, fine aggregate type, there are 2-3 types of fine aggregate we use, different types of cement grades. Of course, here it is single grade, water cement ratios 0.3 to 0.4. So, right, and 21 days, 28 days, 14 days, 7 days, etc., variation we used, and we found this capo test gives us fairly good results. This is the testing that we are doing, drilling hole, surface preparation, and routing the the routing process and all that. So, placing it and then placing the inserts and pull off test also we did similarly, both shows that within plus minus 10% you can get the result. So, this is what finally as you pull it out comes something like this, chunk of concrete will come out, and this is this is how after breaking you get some sort of thing. This is the machine where you read how much kilonewton is the pull out force from where it came out, and the calibration correlation that we obtained was something of this kind. Correlation that we obtained was something of this kind, standard cube test, capo test. So, by and large there is something close to the 45-degree line. So, with plus minus 10% error, right. So, reliability is good, but then European code for example, it says that you establish your correlation yourself preferably. So, some limited amount of code test should also be done with this. This is semi destructive, core is more destructive compared to this, because core would be taking 75 mm core minimum with 20 mm aggregate, where this is only penetrating up to very small depth, So, therefore, you don't get too deep. As a result, this is less damaging and easier to do. Cost wise, still not like, because of the instrument cost, still the cost is similar, not very far different in India. So, correlation shows that it is a good one, right. So, this is correlation with some ACI relationship, bond stress test, that pull off test. So, that is the kind of relationship we have. So, next we will look into code test.